All right, the last lesson for this unit is what we call reciprocal functions. So if I had a function, f of x, the reciprocal would move it from that numerator to the denominator, and it becomes 1 over f of x. So if I had something like y is equal to x squared minus 5, that's the same as x squared minus 5 over 1. The reciprocal of that would mean that 1 goes to the numerator and the x squared minus 5 goes to the denominator. Now, here's an example of a reciprocal function. On the left, we can see the y is equal to x plus 3. And on the right, we can see the y is equal to 1 over x plus 3, where it looks like these two curved lines exist here. My original values I can solve, saying it's 3, negative 2, negative 1, 0, 1, 2, 3, 4, 5, 6. And my reciprocals are, the reciprocal of negative 3 is negative 1 over 3. Reciprocal of negative 2 is negative 1 over 2. Reciprocal of negative 1 is 1. The reciprocal of 0 is undefined because I can't move 0 to a denominator. I can't divide by 0. And then suddenly I keep going. 1 is 1, 2 is 1 over 2, 3 is 1 over 3, so on and so forth. Now, we can see that in the original case, when x was equal to 0, y was equal to 3. Which means that in the reciprocal case, when x was equal to 0, y was equal to 1/3. In my original case, the x-intercept occurred at negative 3. And there was no x-intercept here because I can't divide by 0. So I wind up with what is called a vertical asymptote. A vertical asymptote, or any asymptote, is an imaginary line, like our axis of symmetry, where if I drew a vertical line that ran through there, then you can see that each of these curves is trying to get closer and closer to this vertical line, but will never actually touch it or cross it, because it can never actually equal 3, because that would make the reciprocal dividing by 0, which isn't possible. So we write that as an equation, a vertical asymptote. What's the equation of that vertical line? This is when x is equal to 3. Remembering that any vertical line is always in the form of x equals, negative 3. Now, there are 2 points that occur at the exact same spot on both graphs. You can always see that by looking for when is my original function and when is my reciprocal function the same. Those 2 points occur here and here. Now, why are those points the same? Because the reciprocal of 1 would be 1 over 1, which is still just 1. The reciprocal of negative 1 would be negative 1 over 1, which is still just negative 1. So anytime that y is equal to either 1 or negative 1, those points exist in both graphs. We can see that right here. If I go to negative 4 and negative 1, there's 1 point. Negative 2 and positive 1, there's the other point. If I go into my reciprocal, -4 and -1, there's 1 point, -4 and +1, sorry, -2 and +1, there's the other point. It's the only 2 points that exist in both graphs. Because it exists in both cases, we call it invariant. It does not vary between my original function and my reciprocal function. We also have a horizontal asymptote. It's a horizontal imaginary line where they want to get closer and closer to and will never touch. And that occurs at the x-axis or when y is equal to 0. So when my original function was equal to 0, which is any x-intercept, then the reciprocal function has a vertical asymptote. What happens here as my original function approaches positive or negative infinity, which means my original function keeps going to the left or keeps going to the right, then my reciprocal function is getting closer and closer to the horizontal asymptote, where you can see that it's getting closer and closer here and closer and closer here. For example 2, they're doing the same thing. We're just taking a quadratic function instead of a linear function in this case. So I have my original function, y is equal to x squared minus 4. I have my reciprocal function, which would be y is equal to 1 over x squared minus 4. And we can see that here, here, and here. It splits into 3 sections because there are 2 x-intercepts that change the area or the quadrant that it exists in. In order to find points for my reciprocal function, I would just solve for points on my original function, and then I'm going to take the reciprocal of them. I know that I can't take the reciprocal of 0, so these are the points that make up my vertical asymptotes. My imaginary line that exists here, my imaginary line that exists here, that they're going to get closer and closer to, but never actually be able to touch. We know the y-intercept of my original function is at -4. I can see that right here. The y-intercept of my reciprocal would be at -1 over 4. Right here, or the reciprocal right here. The original one had x-intercepts, where y is equal to 0 at -2 and +2. The equations for the vertical asymptotes are going to be at x is equal to -2 and x is equal to +2. Those 2 vertical lines that I drew. The horizontal asymptote, the point that is trying to get closer and closer to but will still never cross, still occurs in the same spot when y is equal to 0. Now, In example 1 of the previous page, we're able to determine the invariant points of the graphs by using the table of values for y is equal to 1 or -1. Why can we use the lines y is equal to 1 or -1 to find invariant points on the graphs? Well, same reason as before. The reciprocal of 1 is 1. The reciprocal of -1 is -1. How do I find those invariant points on the graph? The invariant points will always occur where my original function and my reciprocal function intersect each other. There's my 4 points. If my original function is equal to 0, then my reciprocal is going to have vertical asymptotes. As my original function approaches positive or negative infinity, then the reciprocal is going to get closer and closer and closer to a horizontal asymptote where y is equal to 0. We call this end behavior, which is going to be a big part of Math 30-1 in calculus. So let's do a quick breakdown of the properties. When f of x is equal to 0, then the reciprocal is going to have vertical asymptotes. When the original function is positive, the reciprocal is positive. When the original function is negative, the reciprocal is negative. Reciprocal does not cause reflections or change signs. When my original function is equal to 1, my reciprocal function is equal to 1. When its original is -1, my reciprocal is -1. These are the invariant points. When my original function increases over an interval, which is a fancy way of saying it gets bigger, then my reciprocal will decrease. When my original function decreases or gets smaller, my reciprocal increases. When my original function approaches 0, the reciprocal function approaches positive and negative infinity, and the graph is going to approach the vertical asymptotes. When my original function is getting closer and closer to positive or negative infinity, my reciprocal is going to get closer and closer to 0 and approach the horizontal asymptote.